Again, my name is Brian Bowen. I'm from Westchester University. It's a state school in southeast Pennsylvania. I'm the mathematics educator there in the mathematics department. My principal responsibilities there are methods and content courses for pre-service and middle grades elementary teachers. And I'm sort of new to the IBL. It's my first conference, but I like to think I've been using some of the principles for a while. My goals for today, in the presentation, I want to share an activity, an IBL type of activity I use in my classes. I like to provide an opportunity for you to engage in some mathematics. I only hope to talk for about a third of the time, maybe a little bit less. And I hope to provide a small amount of cognitive dissonance for your afternoon, small part, all right? So let me set the stage then. During my time teaching pre-service elementary middle school teachers geometry, I observed that they have a bit of a problem with volume formulas. And I don't mean plugging numbers in and getting an answer out. Most of the students I deal with are able to chug through a problem without any issues. They're very good at procedure. But if you were to push their knowledge, understanding beyond just rote doing problems, they run into some issues. So for example, if I was just to ask them the formulas for the volumes for these shapes based on their experiences, they would struggle. And I have some data to kind of support that. When I asked my students, these are sophomore, junior teachers who mostly are going to teach in middle school, if they could recall the formulas for the volumes of these shapes, these are the results I got. And I really want to emphasize as you look at these numbers, these are students who are going to be 2 years down the road teaching my son or daughter middle school mathematics. And they are struggling to recall formulas for volume. And I'm going to attest that less to their knowledge and ability, because these are smart, bright kids. I attest this more to their own K-12 experiences learning mathematics. So when you talk to them and you suggest how they learn these ideas, these formulas, these are some of the things that they talk about. And the main theme that they discuss is this idea of memorization. They're given flashcards, they're given PowerPoints, they're given just these random pieces of information to put in their brain without any concrete connections. So the activity I'm going to talk about today is at least my desire in this activity is try to give them an opportunity to make sense of these formulas so they're not just random letters and numbers, that they make sense to them in some way. So that when a point in the future comes they need to recall them, they can derive them, not just from their memorization, but for what they actually mean. So let me set the stage then. The activity starts with this. We start with the general understanding of what formula is. We build from nets 1 inch by 1 inch by 1 inch cubes, also known as 1 cubic inch cubes. And we use these to start developing the idea of what it means to measure in terms of volume. We fill different shapes. We fill small cubes. We fill big cubes. And we keep putting them in and get to understand what it means to fill in terms of volume. We continue this process with cubes of varying size, 2 by 2 by 2, 3 by 3 by 3. We eventually start talking about a cube that's very, very big. And this idea of volume starts coming back to them. And some start talking about this idea of a volume for a cube or a rectangular prism as being length times width times height. I try to encourage them to think about volume in a different way. Think in terms of cake. If you think of a cube in terms of a cake, you've got layers in a cake. And if we can think of volume in that same way, volume can also be thought as the first layer times the number of layers. Or in other words, area of the base times its height. So this way of kind of thinking about volume is going to help us to make a connection between other volume formulas. It's not a better or worse way to think about volume. It's just a different way it's going to be handy to us. So that's how we start. We then take a next step, and we go from cubes to pyramids. It works out that a pyramid has a different attribute than a cube. It doesn't have the same layers all the way up. You can't think of it that way. But we have the students build a pyramid from paper, which is a pretty significant task when you ask them to build a pyramid the same height and base as the cube they were working with. Because the slant height of a pyramid is not its actual height. There's Pythagorean theorem involved. But they come up with it eventually. They build this pyramid. And they're asked to compare the volume between a pyramid and a cube that have both the same base and same height. And they're provided Cheerios to do this. So some will start picking Cheerios up and put it in both and comparing. Eventually, many will start using the pyramid as a unit of measure or a scoop. They'll start scooping the Cheerios and fill in the cube. And they scoop it again and fill in the cube. Scoop it again and fill in the cube. And when they do that, they wind up seeing something that's pretty interesting. That it takes 3 of those pyramids to fill a cube. And if you work backwards here, that means one of those pyramids is a third the volume of the cube. Or in other words, we could describe the volume of a cube as 1/3 the area of its base times its height. This is a pretty handy formula because pyramids can have different bases behind squares. It's a generalizable formula. And now that third that belongs to the pyramid formula kind of has a meaning to it. We extend this idea then from cubes and pyramids into cylinders. We don't initially fill cylinders with Cheerios, but we start thinking about different ways we could describe volume of cylinders. And maybe you could see this coming in terms of layers. If we talked about cubes in terms of layers, and the layers are the same all the way up in a cake, a cylinder has that same idea. The layers are the same all the way up. And while we could describe the cylinder form in many ways, one of the ways we could think about it is the same way we thought of as a cube. Area of its base times its height. So we've now kind of connected these formulas that were kind of sparing all over the place that are connected in some way. I will give you that most cylinders have a circle as a base. We can definitely go with that, but we can describe it generally as area of its base times its height. Going along the same process, well, if we compared a pyramid to a cube, and we found this idea of a cylinder similar to that of a cube, now we're going to compare a cone to a cylinder. Same process comes up here. We build a cone. It's got the same area as the base and height. We're starting to compare. Kids, before even starting to begin the process, are guessing about the relationship. And they're usually guessing pretty accurately that if you do take this cone and use it as a unit of measure, and you fill the cone and fill the cylinder with the cone, a similar kind of pattern emerges here, that it takes 3 of those cones to fill that cylinder. Or in other words, we could describe the volume of this cone as a third of the cylinder, or the volume of that cone is 1/3 the area of its base times its height. So way back here, we had these different shapes that were very separate from each other, and we're starting to connecting them and showing that they're part of a family. And if you can kind of remember a few little things and remember the connections between them, you're able to come back with these formulas and understand why they exist. So I put the easy work up here. I'm going to ask you to kind of carry a little bit more of the weight. The next thing we do in the class is compare the volume of a cylinder to a sphere. It actually is really hard to make a sphere from paper, so I'm not going to make you do that. But we're going to do that together now. So I'm going to ask you to compare the volume of a sphere to a cylinder in the same way that the kids would in class. They use Cheerios. You're going to use Cheerios. So I'm going to ask you, I don't know how many folks you would be, so we're going to say groups of 2 or 3, to grab one of the gym bags. They're clean. Inside there's a sphere, a cylinder, and Cheerios. And what I'm going to ask you to do is compare the volume of that sphere to the volume of the cylinder. Given we say the volume of the cylinder is area base times height, can you develop a formula for the volume of a cylinder? It may not be the formula you're comfortable with, but a formula that kind of follows this pattern. So groups of 2 or 3, there's a bag there behind you. There's a couple bags here. 2 or 3. There you go. There you go. The Cheerios are about 6 years old. They've been touched by lots of hands. I would not eat them. So what's the volume relationship between that sphere and that cylinder? What's the volume relationship between that sphere and that cylinder? If you haven't noticed yet, the sphere is a half sphere. Pretty good like that, right? Makes it easier to fill, but a little more easy mathematically. So in theory, that sphere is the same height and same base as that cylinder. Close. Keep in mind we're dealing with Cheerios and a wiffle ball, so it may not be exact. There is some margin for error here. Again, be kind. There's a slight margin for error. How many of the half spheres did it take to fill it? So what's the volume of the sphere in relationship to the cylinder? What's up? So yeah, get rid of the change. It's a chew. Yeah. So what's the volume of the sphere in relationship to the cylinder? Get rid of that formula for now. Come back to it later. Okay, all right. Go. Yeah. Should take about 3. Fills out 3 halves. Yeah, yeah, exactly. How many halves did it take? So what's the volume of what's the relationship of a sphere, full sphere, to the cylinder? You're at 2? How many half spheres did it take? So what's the volume of a sphere in relationship to a cylinder that's the same base and same height? Because it's half spheres. Can I stop you for 10 seconds? Our question is not what is the relationship between a half sphere and the cylinder. Question is about the full sphere and the cylinder. So what's the relationship between an entire sphere and the cylinder? How much of the sphere is that of the cylinder? Not the half sphere. So what's the volume of this in comparison to the volume of that? Is the same as this guy. Keep that height thing in mind. It's going to come in later. Keep that in mind. That's the very next slide. Screw your thing up. So what's the volume of the sphere in relation to the cylinder? 1.5 half spheres. What? 3 half spheres. 3 halves. Okay. So what's the volume of a? Remember, like the volume of the cone was 1/3 the volume of the cylinder. The volume of a sphere is what of a cylinder? Pi of those? So how many? So say you filled this. Well, let's go the other way. How much of the cone was the cylinder? So it took 3 cones to fill the cylinder. So the volume of the cone was 1/3 the volume of the cylinder. So this isn't 1/3. What's it going to be? So this is how much of that cylinder? The volume of a full sphere is how much the volume of that. If that's 1, how much is this going to be? Can I ask you to stop a sec? Turn to a group next to you and share your answer with them just to see if you guys compare with the same more ideas. So a group next to you, behind you, in front of you, to left or right of you, see how your answer compares. In front and back, so you come up with. Person in front or back of you, check with another group, see how you came up with, what your answer was. You have none to share with. What'd you guys come up with? How many, what's the volume of a sphere in relationship to the cylinder? What's the volume of the sphere in relationship to the cylinder? Yeah. Good, excellent, good, good. And the cone was 1/3 of it. Can I have you back to me then, please, for sake of time? So what we've just done in 7 minutes is a much more involved thing with students, but this is sort of their relation here. This is their work. They're running out. They're making an argument. They are realizing, and it's a bit of a jump for them that it's 2/3 the volume of the cylinder. That's what the sphere is, and that's an interesting observation. If you look at their work here, they're struggling with this cube thing. Because some of them in their memory are remembering that there is a formula out there for a sphere, right? And the formula for the sphere has got this cube in it. But this is the formula we just came up with. It's 2/3 the volume of the cylinder. The cylinder is pi r squared times height, and this is what we got. And if you go to any kind of textbook, or people are in love with Khan Academy nowadays, right? This is Khan Academy. Khan Academy is telling us that the volume for a sphere should be 4/3 pi r cubed. And yet our work told us it was 2/3 pi r squared times height. They seem to be different formulas. Can you take about a minute and a half more and see how those formulas are exactly the same formula? They are exactly the same. Can you take a minute and see if they're exactly the same? I'm trying to stop you there, but that's right. How are they exactly the same formula? You guys get it? How are they the same? There we go. Good. How are they the same? You were saying it earlier. Like you were saying that the height. But we don't talk about height in spheres, right? We talk about or twice radius or diameter. Yeah. How are they the same? Yeah. All right, for sake of time, I'm going to ask you to come back to me. So you guys are seeing it. It's a pretty nice thing that you guys are jumping to it. This is sort of some of my students' work getting to this realization. That height, when you talk about spheres, is kind of an odd descriptor. We don't usually use height. So we could talk about diameter, and we talk about the great circle within the sphere. But a little bit of algebra substituted in there kind of shows that both those formulas are somewhat equivalent. And backtracking to this idea of 4/3, as we're doing this work, this 4/3 strikes a problem for kids because the volume of a sphere should be less than the volume of a cylinder, and yet this is greater than 1. We can now describe why it's greater than 1. So backtracking real quick, in a very brief lesson or two, we're able to kind of show that these all belong to each other. They're a family, and there's an interconnectedness between them. And then if you can just kind of set a few simple things to memory and some relationships, you can go back and derive any of these formulas you need to. And I'd like to say that with my class, I hope there was some long-term success with this. This is my data from when I was looking at this class. Initially, they didn't perform so well with their memory of this, but right afterwards, not surprising, literally right afterwards, they were able to come with the formulas. But about 5 weeks after, they still were able to come back and describe these formulas with some sense of coherence and conceptual understanding. And I hope that speaks to the power of actually getting kids to inquire, to discover, to think upon their own, as opposed to kind of just telling them ideas to memorize. And that's it. Yeah, thank you. I'll take questions, but I'm also going to take my Cheerios and things back. So before you leave, don't take them with you.
Hi, Anders Hendrickson from St. Norbert College in Wisconsin. So this seems like a great hands-on and heuristic way. And it's the goal you mentioned at the end for these students of having the formulas be something that they can have a few basic principles or ideas that they've encountered themselves, memorized, and then can go back and rederive all 5 of those formulas from maybe
Correct.
2 or 3 basic
Yes.
thoughts that hopefully have
Yes.
lodged in their head. Makes a lot of sense. From my perspective as a pure mathematician, the little gremlin in the back says, well, we've counted some Cheerios and I see approximately 3/2, but is that exactly 3/2 or is it 1.52? So do you have anything else that bridges that, attempts to bridge that gap to get the exactitude?
I don't. And there's a standard of error there that I think we're all going to accept that. And you should see when they start counting the Cheerios initially, it's even worse. Because by the time they get them, there's like half Cheerios, quarter Cheerios, they've shrunk, they've whatever. So I don't. It's a great point. And I guess to some extent, I don't think that necessarily it's my intent. My intent's kind of to unpack their knowledge and kind of rearrange it down that road. That's a good question.
Thank you.
Harold Ryder, UNC Charlotte. I think we all agree that we want our students to think more and remember less.
Yeah.
Are there some other activities that you can point us to that will help us get that point across?
So, I mean, there's a bunch of things. I'm a big fan of the Akel and Wolf book for geometry structures. I don't know if you guys use that. It's an acquired-based approach to geometry. Akel and Wolf, they have a lot of stuff in there. You can imagine there's the whole idea of what area of a circle. We do area of a circle before we do this. We take the circle, cut it into 12 sectors, take one of the sectors, cut in half, make a rectangle out of it, and then we derive the formula for the area of a circle. A lot of my class is just trying to make sense of things that they've memorized. And I feel like if I hopefully I'm getting myself out of a job, because if I can convince them to teach their students like that, when their students get to me, they're going to hopefully be like, I know this, let's move to something else. That's where I'm working towards. So.
Hi, I'm Nina White from University of Michigan. First, I just wanted to say I really liked that this also, besides helping them memorize, remember these formulas or be able to rederive them, that it really emphasizes two really big ideas of volume, the cubic unit, and then also the sort of idea of a fluid filling things and proportional reasoning and all of that. And then I also wanted to say I've tried doing volume from a totally different perspective, and I think mine sort of failed, so I like the idea of bringing them together. I tried to sort of more prove the 1/3 factor. There's a pyramid, a really special pyramid shape called a yangma, which is a square-based pyramid where one edge is actually perpendicular to vertices, and you can actually cut those out and put three of them together to form
as a
a
puzzle,
cube.
yeah.
Yeah, and then you can use other axioms. I use Cavalieri's principle as an axiom to then morph, in our heads, morph that yangma into any other pyramidal type shape.
We used to try to make a sphere and out of Play-Doh, and you put it in the cylinder and you smash it down to see what it would fill.
Oh, yeah.
It sounds better than it works. So.
Well, I thought the Cheerios was a really nice idea, but I just wanted to address like what you were saying about, more closer to
I appreciate
proving
that.
that's another thing you can throw in there that's a little more exact.
Thank you.
Well, they totally believed that pyramid was 1/3 of the square, but then extending that, sort of using abstract ideas to any pyramid type figure is a pretty big stretch.
Hi, this is a comment. Stephen Greenstein, Montclair State University. We had already talked about this, and so I think it's worth sharing with the group. I make the offer so you say the two formulas are the same, and so in my class I distinguish between equal and equivalent, right? Because the formulas are equal. I'm not saying that you're wrong.
Right, no,
I do it for the purpose to say that the way we represent mathematical ideas conveys different insights. So the 4/3 doesn't have any meaning, to me anyway, about why is there a 4/3 in a sphere, but the 2/3 H, like you did, does. And so there's another mini lesson in there about the way we represent our ideas and the insights they allow.
That's a good point.
I'm Dan Goldner, and listening to the discussion, I just got an idea of making yangmas out of stacks of magnets that you could then push into other shapes. I don't know. Because basically I spent more time than I'm too embarrassed to admit how much time I spent on this trying to picture why it's 1/3. And I still don't have a mental picture of 3 cones making a cylinder or 3 pyramids making, it's really hard, but that's the one I want. So now I'm interested in making a mushable yangma.
Play-Doh, too? Perfect.
Yeah, but then is it volume invariant, though?
There
the
you
same
go.
way that, and it doesn't get Cavalieri's if you don't have the slices that stack. Anyway, thanks.
Robert Mendez, University of Houston. Do you have the conversation about, I guess I'd be inclined to say, hey, look, 3 of these fit in here. And so this is going to help you realize it's about 1/3. It turns out that it's actually 1/3. This isn't proof that it's 1/3. So when you're dealing with your students, make sure, so that when they're teaching their students, they don't inherit this kind of, oh, look, it's 3 of them. It must be 3.
So I do it as a sense of discovery about why the formula is what the formula is. I don't use the term proof in anything I'm doing with this. But I want them to get an understanding of why it's 1/3 for the cylinder. And I think it's nice that the relationship between the cone and the cylinder is the same relationship with the pyramid and the cube. It's the same as 1/3. But I don't necessarily say it's a proof per se, but I'd like them to discover where that 1/3 comes from. Thank you, guys.